Hello everyone, my name is Konstantin Vladimirov and welcome back to the master's course in C++ at MIPT. This lecture marks the beginning of another long journey. In the previous parts, we learned about semantic processes, those invisible steps the compiler performs during compilation. And we've seen that for the most part, we don't really control them directly. Yes, we can influence name resolution or type deduction a bit, but only in a rather indirect way. There is, however, one part of compilation that truly is under our control: instantiation. And that's exactly where today's topic lives. We are going to talk about SFINAE and about how it lets us guide the compiler's reasoning at compile time. But let's start with something really more narrow. Let's start with trivially copyable types. Please pause the video for a moment and think, what do you think trivially copyable type really is? 3, 2, 1. Okay. Intuitively, it's a type that you can safely copy with a plain memcpy. If you can use memcpy on something and be sure it is copied correctly, then probably it is a trivially copyable type. And that's the simple idea, but of course it is rather backwards. We need to define those types somehow for them to be safe to copy with trivial memcpy, and standard here makes it a bit more specific. It says trivially copyable types include: first, scalar types. Next, arrays of such types, okay? And next, trivially copyable class types and CV qualified versions of those types. Okay. So the real question is, we sure about scalars, we sure about arrays, okay? Basically, we sure we can copy array of scalars with memcpy, it is okay, but what makes a class trivially copyable? And here's the rule. A class must have at least one trivial copy or move constructor or assignment operator and a trivial non-deleted destructor. Basically, the compiler should be able to copy and destroy it with no user code involved. And now, when is a constructor trivial? And constructor is trivial when class has no virtual functions, no virtual base classes, and no data members with default initializers. And all its base classes must also have trivial constructors. So, if you add a virtual function that is like, you lose triviality because the compiler needs to manage the vtable pointer. And if you write a custom destructor, even an empty one, it's already non-trivial, which usually means the object controls some resource. Because if you're using user-defined constructor, using defined destructor, or user-defined copy constructor, what it means? It probably is some sort of array or hidden array. And memcpy copy would probably break it. So to sum up, a trivially copyable class is one that can be copied bit for bit safely without invoking any special behavior. And that's the key idea. Okay, let's practice a bit. Let's take a look at this example. How do you think? You may pause the video again. How do you think? Is S trivially copyable or not? We have a struct T which contains a constant ref member and a default member initializer. And then we have S, which just contains an array of 10 T's. So, is S trivially copyable? And According to the standard, a constructor is trivial if the class has no virtual functions, no virtual base classes, and no non-static data members with default member initializers. So technically, T here maybe violate this condition, who knows? Please take some time to build your opportunity on this topic. 3, 2, 1. Okay, let's see on Godbolt. And on Godbolt, what do we see? Here, this is stud is trivially copyable of S. And we can see that GCC executor prints 1, yes, trivially copyable, and clank executor prints 1, yes, trivially copy. And what if I make non-trivial move constructor here? Then situation is even more interesting. We can see GCC prints 0. It is no longer trivially copyable, and clank outputs a compilation error. And again, you may score a perfect 10 if you will either introduce the same error in GCC or fix it in clank. Okay, so whom to believe? And we just seen that compilers don't even fully agree on what trivially copyable means with each other in standard. And so if we don't trust them, how could we check it ourselves? It clearly exists and somehow works, but sometimes gives different answers. And what would your own implementation looks like? How would you implement stud is trivially copyable of S? And yes, this is challenging. And now, again, pause this video and think, how can you do it? 3, 2, 1. And if you now gave up, you are correct. You can't. You simply can't implement this yourself. It is just a compiler built-in. And in GCC, for instance, it is implemented with this has trivial copy intrinsic, because it is GCC who knows from inside compiler structures how to implement it. And GCC have not only this intrinsic, GCC have a full list of what is hardwired to the compiler. So has no throw assign, has no throw copy, has no throw constructor, has trivial copy, has trivial destructor, has virtual destructor, is abstract, so on and so forth. We can see the full list in documentation. And even modern reflection, and we will touch upon the reflection soon, doesn't replace that. Reflection still takes to the same intrinsic underneath. But not everything depends on compiler magic. There are things we can reason about ourselves. For example, what kind of entity a name in C++ actually denotes. And it could be an integral type, a functional type, a floating pointer type, an array, or a num, and so on. And probably in some cases, we need to believe to compiler and ask for compiler guys to help with some problematic cases, but in some cases, we can implement some checks ourselves. And in this lecture, we will see how to tell one case from another. And now let's think about those entity categories. If I will say you, something is integral type, something is floating point type, can you figure out all categories in the language? And yes, you can. All categories are plainly listed in the standard. And those they are. There are 14 fundamental type categories in C++, and it's actually easy to remember. The C++ standard itself is ISO/IC 1488 too, and that leading 14 perfectly matches the number of categories. And here they are on the slide. Is void, is null pointer, so on, so on, is function. Everything in C++ falls into at least one of these categories. For each category, there is corresponding trait, a kind of detector. Some of them are implemented directly in the compiler. Some are defined in pure C++. For example, take isVoid. You feed it a type, and if that type is void or const void or volatile void and so on, it returns true, otherwise false. And what is that, mathematically speaking? It's a mapping, a function from the space of all types to the set of true and false. And a type trait, every type trait, is a mapping from types to values. For example, stud trivially copyable v of t takes the type t and returns either true or false. Now, can we make the reverse mapping? Can we go from a value, say true or false, back to a type? And let's think of a types as little clouds and of true and false as two rabbits sitting below them. Each type maps down to one of those rabbits. Float maps to false, and like void maps to true. Basically, everything else except void maps to black rabbit. But what if we want to send the rabbits back up into the clouds to turn a value into a type? And here's one playful idea. Let's say an array of one char represents true, and an array of two chars represents false. That's our tiny reverse mapping. And what about integers? Okay, we could use charge numerals, introduce types that correspond to numbers. For example, an empty struct represents 0, a struct with one empty member represents 1, and so on, so on, so on. And that is exactly how Alonso Church introduced natural numbers in the first place a century ago. But probably you do have some objections. Such reverse mappings are clearly hard to manipulate in the language. And how would you map back from the church numeral? Yes? And arrays, if true is array of one char and false is array of two chars, are a little bit heavy if you want to pass them around as types. And there's a light approach, and that's what we'll get to next. Now think, what could we use instead of an array to encode this idea, to encode types more efficiently? And if you will think hard enough, you probably will come up with something like integral constant. Integral constant take a value v of type t and maps it to type. Integral constant of t and v is a type instance of this template. It's literally a mapping from the value domain, from the v, to the type domain, to the integral constant of t and v. It is basically a way to send a rabbit to a cloud. And inside it remembers everything for the way back from the clouds to rabbits. It stores the value itself. Rabbit is alive on the cloud. It stores the original value type and has a self-alias type, and even defines an implicit conversion to that value type, so you can just use it in expressions like number. That's why you can write things like 7 times an integral constant 6, and it really behaves like a 6. This is cloud which behaves like a rabbit. Pretty nice, right? And of course, the most useful integral constant of all is true and false. For bool, we have two special integral constants, true type, integral constant of bool and true, and false type, integral constant of bool and false. And they give us a convenient way to map types to true or false. That's how most type traits in the standard library actually work. So now the question is, how could we write our own type trait is same so that is same of two same types like is same of int and int equals to true and is same of float and int equals to false? Think about it. It's easy exercise in partial specialization. 3, 2, 1. Okay, I hope you got it right. Notice we still don't need SFINAE. We even haven't defined SFINAE yet. The mechanism here is just partial specialization. We start with the general case, any two different types, T and U for this example, gives us the false type. And then we specialize for the case where both template parameters are of the same type and there we inherit from true type. And that's all it takes. Inheritance gives us access to value, type, and every other members of integral constant, in this case, of true type. So we can write expressions like is same int colon value and not is same char int colon value, a simple, elegant example of how template specialization can encode logic directly in the type system. And writing is same int colon value every time is a bit annoying. So we introduce is same v, a variable template. We haven't really talked about variable template yet, but they're great. Just like we can have class templates and function templates, we can also have variable templates and of course alias templates as well. That gives us 4 possible kinds of templates in total. A nice little grid, what can be template and what can be parameterized with a template. I like to ask about that on exams. And here is same v is simply a shorthand for is same t u colon value. We instantiate it the same way we instantiate any other template. And now we can write assert is same v of int and not is same v of char int, and this works. Much cleaner and much closer to how the standard library does it. And before we move on to SFINAE, let's pause for a small exercise just to make sure we are all on the same page with partial specialization. We'll write our own logical types and not. You see and for any t and u is false, and must be true only if t is true type and u is true type, and not for any t is false and not is true for false type. So think for a moment, how could we implement this using partial specialization? You may pause video here as well, or you may just even don't write it down. Just imagine how would you do it. Okay, I think it is that simple. And at first glance, I believe you think about something like this. And this looks completely fine. The logic seems solid. The syntax is correct. Everything should work. But when we run it and check for this assertion, it doesn't. Let me show you. Okay. You may watch my hands. I do have integral constant here instead of student integral constant, I believe, to be completely consistent with my slides. And this is same. And this is my and this is my not. And please check, this AND is AND. It is true only for true and true. And this not is not. It is true only for false. And now, when I am checking this condition, second test is fail. This AND of is same int and not is same char int is false. It is not true. Let's see tests. Yes, which is false. And here, gtests outputs. This is false. So please think what's going wrong here. And this is a neat, trap. Okay, I believe you got it. The key here is unwrap. You see, this not of is same char int is not a true type, even if it is derived from the true type, because this is like not over true type. And to unwrap it, to feed this NV with proper logic, we need to have also not T template. And that is type unwrap alias template for not of T : type. And now this assert actually works. And V of is same T, not T is same T. Is same T is unwrap for is same. And those triple primary template, specialization, and unwrap template, unwrap alias, jointly called as SFINAE thread. And I will use this terminology in all the rest of the course. And this is a common trap when writing SFINAE code as well. People forget to unwrap, and the specialization silently stop matching. So always remember, define your primary template, write specialization, and unwrap before you use it. Great. And here's a very simple one trait, is reference. We start with the general case. Is reference of T is false type. Then we add two partial specializations, one for tref and one for tref, both deriving from true type, and that's it. How do you think? Will it work? And yes, of course, this works exactly as expected. The compiler recognizes both L-value and R-value references, and if T is not reference, this is just not matched, and then this is false type. Okay. Now let's write remove reference. Is reference is type trait. Remove reference is type modifier. And remove reference is modifier that removes a reference from a type. And if there's no reference to begin with, it just leave the type as is. Like, question maybe posed like this. What should remove reference of int do? Well, there's no reference on int to remove, so the best option is to do nothing. And our primary template simply defines type equals T. And then we add two partial specializations, one for tref and one for tref, both producing type equals T. And of course, we add an alias remove reference T as our unwrap form. Perfect. Now references disappear when they exist, and when they don't, nothing breaks. All right. And now let's try to go the other way, to add reference. We might write something like this. For simplicity, let's just add L-value reference. Add LREF. Add LREF type equals tref. Looks simple enough, but who can spot the problem? The issue isn't with existing references. Those work fine thanks to reference collapsing. So if T is like intref, type is intref because intref collapsed with another ref is still intref. It's perfectly okay. The real problem is, of course, the real problem is with void and its CV qualified versions, void ref, const void ref, and so on. aren't valid types. If T is void, this fails miserably. So this version looks fine, but what do we need? We need if adding reference is impossible, like it is impossible to add reference to void. We just do nothing to be consistent with this logic. If remove reference works this way, why add reference shall work another way? So, how? How will we handle those special cases? And let's try to patch it. Let's set a few specializations for void, const void, volatile void, and const volatile void, so that in those cases we simply keep the type unchanged. This feels wrong, doesn't it? We are like going a wrong way. What is the right way? To understand what is the right way, we need to ask ourselves, what do we really want? And if we hard-coding every possible CV variant, that's usually a sign we are missing a more general rule. And think, what would be right way to express that? And I claim what we really want is to say, if possible, then tref, otherwise t. And there should be a natural way to express this and exactly this idea. All right, let's try something smarter, a devilishly clever trick. What we really want to say is simple. If it's possible to form tref, do it, form tref. And otherwise, just use t unchanged. This version, originally shown by Arthur O'Dwyer in his talk, does exactly that. We define a helper template, ILR_impl, with two parameters. The primary template simply says type equals t, and then we add a specialization that selected only when forming tref is valid. It uses std remove reference t, std remove reference of tref, as kind of proof that tref makes sense. And finally, this add lref inherits from write ILR_impl, and if tref is valid type, the specialization matches and we get tref. If not, the compiler falls back to the primary template and leaves t unchanged. It's elegant but also a bit heavy and not very intuitive at a first glance, and let's look closer at why it works. The key idea here is that one of these templates might just not be usable for a given t. When that happens, the compiler doesn't stop. It simply skips the version that doesn't fit and uses the one that does. And that's why this trick works. The specialization with tref is chosen whenever it's valid and ignored when it's not. So the question now is, what exactly allows the compiler to just skip the invalid template instead of reporting an error? And we'll answer that on the next slide. And of course, let's now introduce one of the most important rules in C++ template mechanics, SFINAE, which stands for substitution failure is not an error. Formally, it means that when the compiler tries to substitute template parameters into a declaration, and that substitution produces an invalid construct, the program as a whole does not become malformed. The compiler simply discards that particular template and keeps looking for others that work. For example, imagine two overloads of function max. When we call it, substitution in the overload may fail. Here, substitution in one failed, and this is okay. The compiler just ignores the one that failed. And by definition, SFINAE applies only to substitutions that happen in the immediate context. You see here In the immediate context of a class function alias or variable template, an invalid construct is forked. And that gives us two questions to keep in mind. First, what exactly counts as the immediate context? And second, what does it mean for construct to be invalid? And let's look at counterexample. Suppose we write a template function that tries to use t::value type inside its body. We then call it with double. And of course, double doesn't have a : value type subtype. But this is not a SFINAE case, because the substitution itself succeeded. The problem appeared only later, during instantiation of the function body. At that point, it's just a regular compilation error. The substitution already happened successfully. And that is why we devoted so much time to the semantic processes. So now you know where type deduction substitution takes place and where template instantiation. And here it is a regular compilation error. It is not a SFINAE. How would we fix it? And yes, we can. If we move the same t:: value type into the function signature, say into the return type, everything changes. Then substitution now tries to form the return types. It fails right there. That's exactly the immediate context that we're talking about. This is invalid, and this is immediate context of substitution. So this time the compiler quietly discards that overload and picks the non-template version instead. No error, no diagnostic, just a substitution failure, and compiler will silently resort to the more convenient overload like this one. Negate with int, perfectly fine, it's just -2. And that's the moment where SFINAE truly applies. The failure happens during substitution, not later, not during instantiation. Okay, now that we have SFINAE, we can finally talk about three separate domains that the language operates on. We already know the value space, our little rabbits, and the type space, our clouds. But there's also a third one, the SFINAE space. The SFINAE space is very simple. It has only 2 points, valid and invalid. Every template substitution lands somewhere in this tiny space. The interesting question is how these three spaces relate to each other. Can we map types to SFINAE outcomes? Can SFINAE results to value, or maybe from validity back to types? If you think about all the possible mappings between these three domains, that's 6 arrows in total, they form the foundation of how SFINAE really works and used in practice. And the third thing we can build is this new SFINAE space is the simplest possible mapping, the one represented by void t. Void t was introduced in C++ 17 and is nothing more than take any pack of types and map them all to void, but only if every one of them is valid. If all substitutions in this pack succeeded, we get void. If at least one fails, the whole construct is invalid. This makes void t a convenient way to combine several validity checks. It's like saying, is this whole group of types valid together? And look how beautifully it simplifies our previously idle-ref example. Instead of this remove reference of tref trick, we're just using std_void t and asking if this tref valid. This is clear way to ask it, and here we're passing void to enable, and if std_void t is okay, then it wins the overload because it's better specialization, not wins overload. It's a little more complicated process. It Compiler just takes this as beta specialization, and we do have our type equal to tref. Otherwise, we have our type equal to t. So void t expresses validity directly in one clean line. And of course, in modern C++, we can go even further. With requires expression, requires tref t is possible, and that's all. We can simply say this specialization applies only if the expression t is valid for reference to t, and that's all we need. No nested templates, no enable tricks. And here, from this code, from this requires expression usage, we have key insight into the true nature of SFINAE. There's an old Soviet cartoon, Holidays in Prostokvashino, and there is the scene where the boy brings home a stray cat, and his mother asks, "What's the point of this cat?" And the boy answers, no, but what's the point of the painting on the wall?" To which the mother replies, "It covers the hole in the wallpaper." And that's exactly what SFINAE does. It covers the holes in the language. It is paper over the cracks. Whenever you see SFINAE in code, it usually means the language is missing something. In most cases, you can either rewrite that code in modern C++ without SFINAE, or go and propose the missing feature to the standard committee. The only honest use of SFINAE is when it really does what its name implies for templates, like template function marks for identical and for different arguments. This is SFINAE as it was designed. But most of the time, like here for stud void t and here and there and everywhere, most of the time, SFINAE is just patching over the rough edges, covering one hole in the language after another. For example, before we had requires clauses, that hole was covered by enable if, and enable if is such an instructive mechanics that I simply can't resist showing it to you. Let's look at another metric. From a bool to one of two types, true, false type, like type name t, type name f. Those two are basically any type. For instance, from bool to vector or list, from bool to int or double, from bool to true type or false type, from bool to any t or any f. This is basic SFINAE mapping. At compile type, it picks of one of two types depending on the value of a Boolean template parameter, and it is simple type level if else. And now imagine the following operation on it. Just remove the second branch. All which is gray on this slide is non-exist. What happens if we make the false case invalid instead of mapping it to type f? Then our mapping becomes mapping from values to SFINAE space, mapping from bool to t or invalid, to valid or invalid, because t is valid. When the condition is true, everything works as before. But when it's false, the resulting type simply doesn't exist. It becomes an invalid construct. And that's exactly what SFINAE can take advantage of. From this idea comes one of the most practical SFINAE idioms, enable if. It turns a Boolean condition into either a valid type or no type at all, and if the condition is true, it yields the provided type by default void, and if it's false, the specialization doesn't define type, so any attempt to use undefined type becomes invalid. In other words, enable if is a way to SFINAE-OUT unwanted template instantiations, to quietly erase the ones that don't meet the condition and keep only those that do. And here's one of my favorite examples. We use enable if to SFINAE-OUT certain template instantiations. For instance, a function that only exists when size of t is more than 4. So if we call it with char, substitution fails. Perfect. But now, what if we want a full coverage? Can we add another overload for the case where size of t is less or equal than 4? And can we make both versions coexist? And of course, in modern C++, it is really easy. You just need requires clause. But back to days where we had a hole in the language, an absence of requires clauses, and we patched this hole with SFINAE. What will you do? Okay, pause the video now and try to build SFINAE style overload set for size of t more than 4 and size of t less or equal than 4. Okay, and you probably came up with something like this. And suddenly the compiler complains, this is not working. And what compiler says? It is really interesting. And compiler complains, let me show you, error. Template parameter redefines default argument. Redefinition of foo. It's really weird. What do we see? This type name and this type name. What's going on? Okay, let's recall the normal process and figure it out. Here's how the compiler actually works. It makes name resolution, collects all overloads with the same name, next type deduction, next instantiation, and probably a loop. And in our case, the failure happens right at step 1 at name resolution. The compiler doesn't even reach deduction or type substitution because the two templates looks identical from its perspective. Default template arguments don't participate in overload resolution, so both declarations collapse into a single signature, and that's why we get a redefinition error, a formal ODR violation. Okay, let's try to fix it. The simplest fix is to add a dummy parameter, for example, an extra int argument with a default value of 0. And now the signatures differ and the code compiles and it works, but it is awkwardly asymmetric. Why here, not here, yes? And the overload has a meaningless parameter, the other doesn't, and this is really ugly. This is really bad. So we want something more clever, and the cleaner solution is to move the condition into the template parameter list itself and make it a non-type template parameter like some pointer. And now the templates are lexically different, so name resolution can distinguish them and everything builds. And in standard, in the ODR part, it is clearly written if two templates are lexically different, it can distinguish between them. Okay, and why do we need a pointer? Probably we don't need a pointer. There are simpler non-type template parameters like integer. And we can simplify further. Replace the pointer with an int entity. And it behaves the same way but looks cleaner, and both overloads remain distinct, and name resolution, deduction, and instantiation all proceed normally. And of course, modern C++ give us a far simpler and clearer way. It requires clauses like this one. No dummy parameters, no pointers, no tricks, just two overloads, one constrained by size of t more than 4 and another by size of t less or equal than 4. And everything is explicit, everything is readable and perfectly defined. That's the proper modern solution. And it shows how far the language has come since the early SFINAE days. Okay, and here's another historical anecdote I can skip. Suppose we want to overload foo depending on whether type T has a nested member of type X or Y. So we write one overload using stud void T if type name T colon X exists. Can you recall what stud void T means? It means if this is valid. If this is valid, pick this overload. If this is valid, pick that overload. At first glance, it looks completely reasonable, but when we try to compile it, we immediately get really cryptic error. Let me show you. It is beautiful. Let me show you example. This struct 1, it have subtype FST, and this have subtype SND, and this overload is valid if TFST exists, and this is valid if TSND exists, and everything shall work, but it don't. And why? So let's ask a compiler what's wrong, and template parameter defines default argument, but this just worked. This just worked at SFINAE. Why? Why candidate template ignored here? And here again, redefinition, and previously declared here, no matching function, and so on. So we have something really strange. The problem is that void T is just a type alias. Sorry for this. Aliases are substituted before name resolution. So both of our templates end up looking identical. Each effectively have a parameter of type void, from void pointer in this case. From the compiler point of view, the signatures are the same. That's why it complains about redefinition. And it's a subtle but very instructive example. Without a clear understanding on when alias substitution happens, this error feels completely random. But with the knowledge, the whole picture makes sense, and there's even an elegant historical fix to it. And this is Huggins' trick. A small materialization of void T solves the problem. The idea is to materialize void T. Instead of being a plain alias, make it a dependent type that inherits from stud type identity. And now the two overloads are no longer identical because, let me show you, because this is void and now this is struct, and this alias disappear, but struct here remains, and is same v works as usual, but in this case everything works. And probably if standard committee think a bit, void T would become like this, like Huggins void T from capital A. But you can do it yourself. It's just as simple to implement, but it saves us from surprisingly tricky bugs with aliases. That is why aliases have bad reputation in the language. And let's take one more short historical detour. Move only function. Stud move only function reveals something beautiful about C++ type mechanics. And imagine we do not have move-only function in our language, because in C++23 we do have move-only function. There is no point to implement it. But imagine we don't. And regular function will not work if closure is not copyable, if closure is movable. And error is use of deleted function inside the closure. So, if you try to capture a unique pointer and assign it to stud function, the compiler complains. And let's sketch our own function that solve this problem. Let's sketch our own move-only function and see what hidden language ideas it brings to the surface. And all right, let's start simple. Here's the skeleton of our move-only function. We got a closure stored on the heap, probably somewhere inside this unique pointer, managed by unique pointer with a custom deleter, and the invoke pointer knows how to call the function with this closure as implicit argument. And if anything looks strange, don't worry. We'll unpack it step by step. But now, first step of unpacking it. Do you know what this tiny plus sign do? Oh, that's the positive lambda hack. It forces the lambda to decay into a plain function pointer. So we can store it as a regular deleter in the type raised unique pointer. And so far, everything we need is here. We can heap allocate the closure, we can destroy it through this any deleter, and we know how to call through invoke. And the only thing missing now is the call operator. How do we actually implement this? How can we do it so that it calls the stored function with the given arguments, like this args? Because this is primary template, this is partial specialization with return type and arguments of function type. This partial specialization replaces t with function type, so it is definitely more special, it is less general. Int will be here. Int of int and float will be here. Pause the video for a moment and think, how would you write operator braces? How would you write call operator? 3, 2, 1. All right, let's try to make it callable. The simplest idea is to define function call operator, which just calls invoke of this unique pointer.get and args with variable pack expansion. Straightforward enough, right? Of course, here and everywhere, we silently assume that you write the proper forwarding, like those args are args ref parameters, stood forward of args of these args here in invoke. You need to write ref and stood forward everywhere. I just skip it for now because otherwise my slides would be all stood forward. So it's just to make things simple and clear. And now what happens next? We call invoke, we get the result. And then we clean up. We clear the pointer and reset invoke to null pointer. That's because our move-only function should only be callable once. The stored callable is move-only, so after the first call we destroy it. There are a few issues though. First, no except. Don't rush to put it there. No except must always be justified. It's a strong promise. And second, can everyone see in which cases this operator still won't work? Pause the video now for a moment and think, when would this implementation break? 3, 2, 1. Okay, I hope you guess. There are two different functions in C++, those that return void and others. And our move-only function with this operator works fine until the callable returns void. And the moment it does return void, everything falls apart. We can't store void in a variable. We can't assign it. And the compiler immediately complains. And so this whole design implicitly assumes that the return type is something we can actually hold. In other words, it only works for function that returns something. But in C++, there are functions that return nothing. And looks like it's time to fix that. And yes, you already know the trick. Probably we'll use SFINAE to patch over this crack. Right. One overload for the call operator for non-void return types, not studies void v under student enable if, and other studies void v under student enable if, we just invoke and then clear. Okay? The idea is simple. If it is not void, we call and return result. If it is void, we just call and clean up, and looks perfectly reasonable. But will this compile? And answer is no. And let me show you an error, because this is really instructive error. Let me show you a good bolt. Okay, so this is something like our move only function. This is unique pointer, this is invoke, and this is our constructor from any callable, and this is our function call operator overload, this and this. And from this red underline, you can immediately guess something goes wrong. And let's figure out what. And compiler says us, wow, what error? No type, name type in student enable if false int. Enable if cannot be used to disable this declaration. What? And what about GCC? Maybe Clang just go mad. And GCC is even worse. No type, name type. But there is a type in student enable if, and of course in student enable if false there is no type. But this is the point. You want to SFINAE-OUT this thing. For SFINAE-OUT to work, the language construct must become invalid. And in order to become invalid, it need to mention a non-existent type inside student enable if. What's wrong? It's really, really mysterious case. It says something like enable if cannot be used to disable these declarations, which sounds almost ironic, as if the compiler completely understands what we are trying to do, but just refuses to cooperate. The reason is subtle but familiar. This check doesn't happen in immediate context. Our enable if lives in the template parameter list of the member function, but not in a place where the substitution failure can quietly discard the overload. In other words, the compiler is too eager here. It tries to resolve enable if right away before substitution. And that's the key idea: laziness versus eagerness. When will this check actually be deferred? When will it become the part of substitution context? That's exactly what we need to fix next. And this technique is known from the old days as trampoline SFINAE. We introduce an intermediate type like R2 whose resolution must wait until the point of instantiation of this method. And here R2 is equals of to R, and of course this student enable if is now as SFINAE. It is now inside the immediate instantiation context. It is SFINAE, it is not a compilation error, and this works, but this looks really ugly. And in the world of the modern C++, we just don't need it. No trampoline required, because we do have requires. This is a function call operator, and requires, this is not, is void, and this operator requires, this is void, and that's all. And just compare how clear and elegant this solution compared to these trampolines SFINAE with those awkward types just to like workaround language semantics. This is what I'm calling elegance of modern C++. And now let's take a step back. If you look closely at conditional T or neighbor if, they start to look like something else entirely, as if there is a tiny programming language secretly living inside C++, a language with its own conditionals, recursion, and functions. Only everything happens during compilation. And that hidden language was discovered by Erwin and Ruch back in the early 19th. He wrote a C++ program that didn't run at all. Instead, it printed prime numbers as compiler errors. Every prime number appeared right inside the compiler diagnostic output. This blew everyone's mind. The compiler could actually perform computations, and thus template metaprogramming was born. From there, it was only natural to ask, if we can compute primes, what can we compute else? For example, can we compute factorials? And we can, recursively using templates. And we close the recursion with this full specialization of 0. As the result, this is integral constant, which recursively uses integral constant of n-1, n-2, and so on, until it reaches the factorial of 0. And this factorial of 5 colon value gives you 120, computed entirely at compile time. The idea of doing anything at compile time was revolutionary. It meant the compiler itself has become a programmable machine. But this approach has side effects. Templates were never meant for arithmetic, so computing something as simple as Fibonacci numbers meant deep recursive instantiation. And yes, compiler would happily reach their recursion limits and crash. Here's a particularly inefficient but famous example. A template computing Fibonacci numbers modulo m. It works recursively. Why modulo m? Just to avoid overflows, yes. We don't want to work with integer or unsigned overflows. And Fibonacci modulo m is still infinite sequence, like modulo 10 or modulo 20. So, and surprisingly, it still finishes, because if you will write like executable program in C with this tree-like recursion, it will never end. It have a runtime proportional to n factorial for nth Fibonacci number. But this still finishes because the compiler caches instantiations. Once a template for some mth Fibonacci number is instantiated, it is never created again. That's part of the language rules. So this monstrous recursion eventually converges. What do we have in modern C++? Today, of course, we don't need any of that. What once required a whole meta language inside C++ can now be expressed with a single constival function, which happily calculates Fibonacci numbers, and constival says this function must run at compile time. No special templates, no recursion depth errors, just normal code that computes during compilation. And here's the fun question. If we implement Fibonacci both ways, the old metaprogramming way like this, and the new constival way like this, which one do you think will be faster to compile? Which one will faster gives you, like, I don't know, 1 millionth Fibonacci number? Please make your experiments and write results in comments. Okay, and let's take a step back and organize everything we've seen so far, because next time we will be moving through the same territory again, but already from a modern perspective. We can think of C++ as having 4 computational quadrants. The first one, compile time computations, We have things like constable or Fibonacci, where all work happens entirely during compilation. The second runtime computations, everything happens when the program runs, and this is traditional, familiar world of execution. Then we have type transformations, operations that exist purely in type space, like add a value reference to type t. You can't write a constable function to add a reference to type because it's not a value operation, it's type operation. And finally, the most intriguing quadrant, mixed computations. This is where compile time logic interacts with types and values, where we blend all three domains we've already discussed. That's where the real magic begins, and that's exactly where we are going next. The first person who really approached mixed computation, or at least came very close, was Andrei Alexandrescu. In 2001, I believe, he published his legendary book Modern C++ Design. By the way, a small piece of advice for everyone. Never, ever call your own book modern. 15 years later, it will sound ironic. The key idea of that book was the type list. A type list is a compile time linked list of types, each node containing a head and a tail, which itself might be a type list. So you can peel off the head type, and what remains is another type list. Loki library introduced macros like Loki type list of 4, which build such lists, and algorithms like Loki reverse, Loki type add, allowing it to reverse the list to extract, say, the search type. And Loki caused a sensation, not because it was immediately practical, it wasn't, but because it showed something entirely new was possible. Types could be manipulated like data. And just 2 years later, David Abrams and Alexei Gurtovoy published the MPL book, presenting the Boost MPL library, the first truly practical metaprogramming toolkit. Now we could create MPL vector of int, long, float, and double and apply algorithms like MPL transform to transform it to int pointer, long pointer, float pointer, double pointer list. MPL offered indexing, searching, and even MPL colon find. It makes working with types as straightforward as with values. And let's solve some real task using MPL. A compile time mapping. Imagine we have MPL vector C, compile time vector, of char of int, 1135 and these two big numbers, a list of tags, tag IDs known as compile type. We define a structure tag entity that stores a Boolean flag and a string. Then we define a fixed message container that maps each tag ID to its entity. If we call fixed message dot get tag entity of 11, we get the tag entity stored as 11. Those like indices, and those are fixed mapping. We are in the regular array, we are mapping 0, 1, 2, 3, 4 to structures. And here we are mapping 11, 35 to structures, not using a lot of space. We are using only space for 4 structures at the runtime. And if we call get tag entity of 13, it will not compile because 13 isn't in the list of known tags. So the indices are fixed in the compile time, but the data itself is mutable at runtime. A perfect example of mixed computation. Under the hood, MPL performs the compile time part. Let me show you. I believe we will see Compiler Explorer shortly. And yes, here we are. How it works? How would we implement this using Boost MPL? You see this bunch of inputs, and this is fixed message. We have common text count, old style like Adam not even not context print, old style program. Okay, before C++11 even. And then we have index, and index is MPL find from common tags MPL integral C int tag. So we are just looking for position of this tag, type colon colon post colon colon value, position of this tag inside common tags. And we have static assert that tag not found if tag is not found. And then this get tag entity is really simple. We have this index of our tag list. So 11 is mapped to 0, 35 is mapped to 1, and so on. And just use it to access common text array. And common text array is just std array. It is really cache friendly. And here we can do things. We can create this container, operate on it, even change data at runtime. It is a real mixed computation example. Okay, but MPL wasn't the end of the story. The next big step was Boost Fusion around 2008, I believe. And still before C++11. Fusion was truly ahead of its time. It let you manipulate both types and values in one framework. You can have a fusion vector like this, and then at compile type, filter out all floating point types, and at runtime, process the actual values. This was in essence a stud tuple 3 years before stud tuple appeared, and really more convenient, just longer to compile. And Fusion transforms values at runtime, but types at compile time. And let me show you one more, because it's too good to skip. We create a Fusion vector, push something into it, check its size, its last element. Everything looks like runtime work, but all of that still happens with compile time knowledge. It looks like regular code, but it is a metaprogramming. The very essence of mixed computations, compile time types, runtime values working together. So let's solve something fun using Boost Fusion. Suppose we want to compute a Euclidean distance in an n-dimensional space. Everyone remembers the Pythagorean distance, right? Exactly. The square root of the sum of squared differences. So, for example, we have two tuples of doubles, and Pythagorean distance should give us 2. Please check yourself here. And if we have three-dimensional tuples, this is 2 as well, because third dimension of 0 adds nothing. Okay, how can we write such a generic function without index sequence, without manual enrolling, and so on? Exactly, using Boost Fusion. So here's the idea. We take P1 and P2 and build a fusion vector of references to them. That's our ZIP-T. And then we call fusion fold on a fusion zip view of that vector. And we start with 0 and use a small functor, Pythagoras, to accumulate the square differences. This fold takes this functor and this initial value. And how would we implement the functor? Really simple. Fusion at 0 axis minus fusion at 1 axis. Return arc plus d times d. And it is straightforward. It subtracts corresponding component and adds up their squares. And the neat part is that Fusion lets use the same code for any structure that behave like tuples. We are not limited to stud tuple at all. You usually have a struct say, a point with x and y. Now, Fusion has this wonderful mechanics called struct adaptation. You just tell it this structure behaves like a tuple. And from that moment on, Fusion knows how to work with it. So once you adapt your struct, you can pass it straight into the same PyDist function. No changes needed at all. You can now compute the distance between 2 points exactly the same way as between two tuples. That's the beauty of Fusion. You write one algorithm and it automatically works for any type that can look like a tuple at compile time. And that's a perfect place to wrap up. This is what real metaprogramming tool looks like, where type level and value level computations finally meet. So, what do we have so far? We've met SFINAE, that ancient and honorable trick that used to patch the language in places where features were still missing. And we've seen how far metaprogramming can go all the way to boost fusion, where types and values finally start to live side by side, I would say. And yet, even that isn't always enough, because we haven't seriously used const export yet. That's where we are heading next, to the modern world of real compile time computation. No homework for this lecture. I hope you're busy with your current assignment and some bibliography. The C++ 17 marks the end of SFINAE and enable if h. Everything we discussed today fit entirely within this version, before constival, before reflection, before concepts, and so on. Of course, I need to recommend you Andrei Alexandrescu Modern C++ Design. Modern 2001. Modern. This book essentially invented practical metaprogramming, type list, policy classes, traits. This is where it all started. Abras found Gurtavoy template metaprogramming. That's the handbook of the Boost MPL era. It teaches how to build compile time algorithms and structures systematically, a whole parallel world inside the compiler. And then this talk, one of my personal favorites, solving word problems with Fusion. Pythagorean distance is taken by me from this talk. Michael Case is awesome. And this an excellent consolidation and good and really big, really like overwhelming, I would say, book from Vandervoort and Yossiutis. C++ template, the complete guide, and it is exactly the complete guide. And great talk of Louis Dianet, metaprogramming in C++ 14, a bridge to the modern view. He shows how many old template tricks can be expressed more clearly with like constant expressions. And finally, I would recommend you a talk by Arthur Dwyer. I already mentioned Arthur Dwyer in ILR Impel hack. And this is talk where this hack was introduced as soupçon of SFINAE, like soupçon in French. One of the last deep dives into the topic. After that, the focus gradually shifts, not because SFINAE vanishes, but because the language finally gave us cleaner and more expressive ways to achieve the same goals. That's all for today. Thank you, everyone.